Hello everyone, this is Giacomo speaking for ESO, and welcome to the new event of the ESO Hypatia Colloquium 2022. We are very sorry, as today we will have only one talk, as one of the talks had to be cancelled at the last minute, but we want to congratulate and welcome, of course, the speaker of today that will be introduced immediately by Tommaso, who is a ESO fellow who kindly volunteered to chair the session. Just let me give you very, very briefly the usual technical details. That the event is happening on Zoom and streamed on YouTube. So participants that are on Zoom, please be aware that this event is streaming on YouTube. If you are uncomfortable with that, you can leave the event and then join by watching the event live on YouTube, where people can also ask questions or make comments using the live chat, while the ones that are connected on YouTube, on Zoom, they will be given the chance to make questions at the end of the talk by Tommaso, the chair of the session. And please as always, please have a look at the program that is available online, where you can. For each of the talks, there is a link where you can download the PDF of the curriculum of our speakers, and soon we will publish also the proceedings of the Hypatia 2022. While the proceeding last year is still available online, you can download the PDF and read all the beautiful contributions by our excellent speakers. And with this, I think I will announce, as usual, as this time of the year, I would like to announce that we have the studentship program is open for application. You can apply if you are a PhD student and you would like to spend from 6 months up to 2 years at ESO Garching or ESO Chile. You can apply, and all the information are available online, and the advertisement is on the ESO job vacancies webpage. So please have a look. If you have information, don't hesitate to contact us. We are looking forward to host you at ESO to make your scientific PhD with us. And with this, I will leave the floor now to Tommaso for the real introduction to the event. And thank you very much.
Thank you, Giacomo. Hello, everyone. My name is Tommaso Marchetti. It's my great pleasure to be the chair of today's session. And so the speaker of today, as Giacomo said, we only have one speaker, is Alfred Castro-Ginard. Alfred finished his PhD in Barcelona in 2021, where he worked on the detection and characterization of open clusters using data from the European Space Agency satellite Gaia. And also, he used open clusters to learn and to say something about the spiral structure of the Milky Way and the Milky Way as a whole. So after his PhD, Alfred started a postdoctoral research position at Leiden Observatory last year, where he's now working on the characterization of the selection function of Gaia. And today's talk from Alfred will focus on the open clusters. So Alfred, maybe you can start sharing your screen. And whenever you want to start, the stage is yours.
Okay, thank you. You should see the screen, full screen mode now.
Yep, thanks.
Right. Thank you a lot for the introduction. That saved me a couple of minutes of my talk. Actually, well, I wanted to thank the organizers for the opportunity. I think that's a very nice initiative for young career and for young researchers, and I'm glad to be speaking here today. The way I will talk about our last work on the detection of open clusters using Gaia data. First, a bit of an introduction, very short. So what is an open cluster? An open cluster are stellar groupings, right, of stars that were born at the same event. They're usually young stars, and they share common location, velocity, age, and initial chemical composition, among other things. And in terms of Gaia observables, that are what we are interested in here, is the first time we can describe open clusters in a 9-dimensional space. That means we define or we describe open clusters as stellar overdensities in the astrometric space that will mean position, parallax, proper motion, and type velocities, even though for our work here, we don't use radial velocities because they are only available for a small subset of the data. And also we can describe these open clusters following an isochron in a color magnitude diagram, and that are the extra 3 dimensions, which is the 3 magnitudes of Gaia. And what is Gaia? Probably I don't need this slide anymore because it's well known, but just in case. So Gaia is a space-based observatory, right? With the main goal of mapping the Milky Way. It has different data releases that were delivered in different stages. So we have the DR1, where it contains like billion sources, but only parallax and proper motions for around 2 million that were in common with Tycho, Hipparcos, sorry, the predecessor of Gaia. Now we have the big release, DR2, that is actually what I think it changed the game in open clusters science, for instance. That was billion sources with parallax and proper motions. The later release, that was EDR3, was almost a year and a half ago. Has basically the same information than in DR2, but with improved precisions for parallax and proper motions. And in less than 1 month, that would be the third release, the full third release, that will also include what is relevant for us in this case, same information than DR3, but with a bunch more of radial velocities. Okay, so what we're talking about is the method we developed to detect new structures in Gaia, new open clusters in Gaia, and it is because we have a large amount of stars with a very good precision in position, parallax, and proper motions, and also the photometry. So basically what we did, it was we devised this methodology and tested in the TIGAS dataset, which was the first data release of Gaia. Then we adapted to the methodology to work in Gaia DR2 to adapt for the huge volume and the high density of the regions I wanted to analyze. And for that, we needed like a big data framework that we'll explain afterwards. And then we also want to expand in our last work, the census, using Gaia EDR3 because of the improved positions in parallax and proper motion, basically. And we did this with the goal of testing the hypothesis of open cluster population completeness in the solar neighborhood, maybe, basically. I will also give a few words about this later. And yeah, we realized that when trying to characterize, so there were a list of non-open clusters previous to Gaia, and we tried to characterize them using Gaia data, but only around 50% of the objects were found in Gaia, and plus we serendipitously found around 60 new objects, so that was already encouraging that our work will be important to do. Okay, about the method, we call it OC Finder, Open Cluster Finder. That's a data mining methodology, automatically search for open clusters in the Gaia archive. It's a combination of two machine learning methods. First, we search for overdensities in the astrometric space. That's what I said in the introduction slide. So we have positions, sky positions, parallax and proper motions. And in this 5-dimensional space, we search for stars that are closer together than field stars. And for this, we use the DBSCAM methodology, which is a density-based space clustering, basically. I will explain also more about this a few slides later. And then the second step is, okay, we have now the overdensities. Now we want to see if they actually are real objects, real physical objects, or they are just random statistical overdensities. And for that, we train a neural network to detect the isochron patterns that open clusters define in a color magnitude diagram using Gaia photometry. Okay, this is an overview of the whole methodology. I will explain step by step later, but just let me give you the big picture. So we start from the Gaia data, basically. Then we do some preprocessing steps, which are common in every machine learning pipeline. After this preprocessing, we run the DBSCAN, I told you about, in each of the sky regions. We shift these regions and run DBSCAN again, just to account for clusters that might be in the border of the regions, and we don't want to bias because of that. That provides a list of DBSCAN clusters that may be real physical objects or random statistical ones. And we use a neural network trained with known well-studied clusters with Gaia photometry to finish with a list of new clusters. Okay, so going step by step. First, the preprocessing step. This is an important step, even though it's usually like not talked about, but it's an important step. So we basically focus on the galactic disk. This is a plot showing data in TIGAS basically, and this is the grid we use to search open clusters in. Why do we want to split the sky in these small regions? Well, first, because we don't expect clusters outside the galactic disk, so we are only looking at clusters within plus minus galactic latitude of 20 degrees. Most of the clusters are there, so we expect clusters to be there. And also we want to define these small regions because we are using a density-based algorithm. So this relies on finding overdensities over an average density, right? And if we define an average density, which is the whole of the galactic disk, then the overdensities that we will find will not be representative, basically, on these open cluster scales. So we divide the whole galactic disk into these small regions to define an average density into these regions and find meaningful overdensities there. Okay, to every of these smaller regions, we applied the DB-scan algorithm. This is a sketch of how the DB-scan works in 2 dimensions. I have to say that we do it in 5 dimensions. I cannot plot 5 dimensions. Okay, why do we choose DB-scan? Because it's convenient for us, because it requires no a priori knowledge of number of clusters we want to find, as this is a huge difference with other clustering algorithms. We don't know how many clusters we're going to find, so that is convenient. It can find also, because it's density based, can find arbitrary shaped clusters. So this is, for instance, comparing with Gaussian mixture models or something that you are limited to a Gaussian shape. So this can find arbitrary shaped clusters. And we need to define only 2 parameters, which basically define the density threshold where we want to find the clusters over this density. And for the rest of the talk, when I'm using distance, so we're using the notion of distance between stars, I will use this Euclidean distance in 5 dimensions. It's not the sky upper distance or something. All right. This is basically a graphic view of how DB-scan works. Basically, it goes point by point, in this case, star by star. Define this epsilon neighborhood around the star and see how many stars can we find in the neighborhood. If the number of stars found in the neighborhood are higher than a certain threshold that we define, then this is considered a cluster. If there is no stars or not as much as we would like to, then there's field stars. Okay, so how we define this density threshold to find clusters? Well, I said that we have 2 parameters. So for the DB-scan, we have epsilon and the minimum number of points, but we also have the sizes of these smaller regions that we define, right? So the minimum number of points and the sizes of these small regions are optimized using simulated data. So we chose several of these values that perform optimally, so can recover as much clusters as possible, and we use those values. Sorry. And then for the determination of the 3rd parameter, which is epsilon, we do it automatically in each of these boxes. Basically, we use the fact that stars within an open cluster are closer together than field stars. This can be seen in this diagram here, this histogram here, where I plot the distance to the 7th nearest neighbor in this case. And we see this blob here around lower epsilons that belongs to an actual open cluster. And we want to isolate this blob by comparing to the field distribution that will be the orange one, and then just basically take a value of this epsilon, sorry, that will be the threshold where we want to detect open clusters. Okay. We do this clustering step in a big data framework. That is because we have a huge amount of data. We go up to magnitude 18. That means we're having several hundred million, sorry, of stars, and we want to do it all of this like optimized in a big data framework. And for that, we use Mare Nostrum supercomputer. This is located in Barcelona. The main characteristics here at the characteristic I like the most is that it's located inside a chapel. So it is a very beautiful supercomputer. So if you have a chance, you can visit it. It's not just me that says that it's a very beautiful computer, but it's been chosen as the most beautiful data center in the world. So I really suggest to you, if you are in Barcelona, just drop by and visit it. Okay, so we ran DBScan in each of these, in the whole galactic disk. In fact, we did it first at magnitude 17, but then with EDR3, because of the improved precision, we do it in magnitude 18, which is basically, as I said, 100 million stars. And okay, we divide the sky in these small boxes, but in each of these boxes, we have up to tens of millions of stars. So that is a lot of data. So that is why we need to use this big data. And it is an advantage now from our method compared to other methods for similar purposes, where they can only analyze around of the order of 100 or tens of, 1,000 or tens of thousands of stars. We are tens of millions. So that is also an improvement that will prevent some biases. Okay, so now we have the overdensities. Might be real objects, might not be real objects, might just be random statistical overdensities. And this will be these two cases I show here. So in the left, you have a real object, real open cluster color magnitude diagram. You have all this nice isochron. And in the right, you just have random stars statistically. I mean, they are overdensities, but not belong to real objects. So we want to distinguish into these two cases. And for this, we use a neural network. In fact, this is just took from Google, but it's a very similar one. So we have a set of convolutional layers that can extract the minimum features, the meaningful features to be learned. And then we have in the last layer that will be represented here by the green dots, we have the actual classification. And in our case, the red dots is not from 0 to 9 because this is a handwritten digit recognition. In our case, it's just cluster or no cluster. And for that, to train the network, we use a color magnitude diagram from real open clusters known, well studied with Gaia photometry, but also we use simulated isochrons from the Padova database, and with a huge range of ages and solar metallicity and the distance where we expect to detect the clusters. Okay, so these are the results. This is running our methodology to the known clusters we previous to Gaia, basically, that were determined, that were characterized with Gaia DR2. Basically, you can see three kinds of clusters here: the ones that we can detect, the ones that we don't detect on the clustering algorithm, so we don't detect at all, and the ones that we do detect on the clustering algorithm, but they don't go through the photometric validation. Basically, what we focus here, so the size of the dots here is proportional to the contrast of the cluster field. So the bigger size means like a dense cluster on a sparse field, let's say, so it's easy to detect the cluster. And we see here is that what we detect are usually more compact objects with respect to the red dots here that are smaller. So we don't detect them because they have more compact object in the neighborhood. But still, I think we do like a good job detecting high percentage of them, of the known ones. And this is basically a summary of the results. So in DR2, we're able to detect around 650 new clusters. Sorry. First in TGAS, then in anti-center direction in DR2, and then in the whole galactic disk using this big data approach. And then a surprising thing is that in DR3, we can detect more or less the same amount of clusters. And this is, of course, we go magnitude fainter, so we expand the volume where we search for these clusters, but also because of the improvements on the precision of the parallax and proper motions. It says submitted here, but it's actually accepted. It's not published yet, but it will be. It's on archive. It will be published in Astronomy Astrophysics in the coming days, I guess. And this is a bit how the results look. So basically, we see that the clusters we detect in this left diagram are farther than 1 kiloparsec, let's say. That will be belonging to parallax 1. We can also see this in the right diagram where we have around the solar neighborhood, that will be, the sun will be at 0, 0. We have like this circle with no black crosses that will belong to the new clusters. And that is what I say basically, because we have better positions in parallax and proper motions, and we go 1 magnitude fainter, and that naturally expands everything to further distances. And here it shows the improvement of the clusters found. In orange, this is the proper motion dispersion of the open clusters in DR2, and the blue ones is the proper motion dispersion of the clusters in EDR3, and you see that the improvement, I mean, the dispersions are lower, especially in proper motions. That is what allows us to discover many more clusters. Okay, this is parentheses on this. I've described the DB scan, which is basically you have to define epsilon, a minimum number of points, and that defines one density threshold. But there is also another methodologies, for instance, HDB scan, that it allows you to build a hierarchy of density thresholds, let's say, and find clusters with different densities. We use that for membership characterization in this diagram here in TARIC Collaborators 2021, where we knew where the cluster was and applied DB scanning in the neighborhood, and then improve the membership characterization. And we also applied this in Casamiguel and Collaborators 2021 to test the strong chemical tagging, the possibility of a strong chemical tagging. So we use the chemical space with high precision abundances to recover the clusters that we introduced in the sample, and we saw that except for the clear cases, we cannot recover them, and that throwing some doubts on the strong chemical tagging. But anyway, it was just a parenthesis. Okay, so now we have the cluster population, either if we detected it or not, and we want to compute, we want to do something with these clusters, and for that we need astrophysical parameters, right? So we compute it in a neural network also trained with well-characterized cluster with AGs, distances, and line of subdistinctions. In this case, we train a neural network using these clusters to estimate unknown parameters, parameters of unknown clusters that we discovered or any other group discovered. And this is basically the results. We could estimate AGs, distances, and line of sight distinctions. We saw that in this case, sorry, this is a diagram of the galactic height as a function of the galactic radius as a function of age. We saw that basically more or less it follows what was expected. So no high latitude clusters in the inner galaxy, except for these ones, which are quite interesting for follow-up studies. Also, we can see the flare towards the outside galaxy. But more importantly, or what I'm most interested in, is that if you divide these clusters in different H pins, so you can see a hint of some structure here that we can relate to the spiral arms, right? So if we focus on the lower left plot, where we have the clusters with ages lower than 100 million years, we can see these overdensities that are close to where the spiral on the spiral locations. And we want to explode that. So basically, what we did is we want to detect now overdensities, not of stars, but the overdensities of clusters. We will use young copper clusters, so clusters with ages lower than 30 million years. Where so if we suppose that clusters are born in spiral arms, they will remain around the birth location in this time frame. Right? So we detect these overdensities in this space, and we assign the overdensities to the different spiral arms. And then we feed the usual log periodic spiral arm to each of these over densities. And we did it for the Perseus, Locker, Sagittarius, and Scutum arms. And then this added to traditional tracers of spiral arms, which are these high mass forming regions. We could fit this log periodic spiral arms and get the parameters for the spiral arms in the solar neighborhood, basically. And now what we want to do.
Sorry, yeah, it's the 20 minutes past. So
yeah.
Minutes. Thanks. Sorry.
No, so now with this information that we have on a present day structure of the spiral arms, we want to trace a little bit the evolution, because we also have like a subset of these open clusters tracing the spiral arms have radial velocities as well. So we could integrate back and see the evolution of these arms. Basically, what we do here is sketched here. So we have in the blue line, solid blue line, is the position of the spiral arm today. The black cross is the open cluster that was assigned to the spiral arm. Basically, what we do is integrate backwards the orbit of this open cluster using the positions, probability motions, and radial velocity. And then when we have the birth position of this cluster, we suppose that this is a spiral arm, and we evolve forward this spiral arm using circular rotation. So we want to compute the speed of this spiral arm pattern. We do this iterating over different Monte Carlo realizations to find the optimal pattern speed. And this is what we find. So we find that each spiral arm has his own pattern speed, which is different from, it's not a global common one pattern speed that will be related to the density wave scenario of spiral arms. So we found that every spiral arm has his own pattern speed, and that it follows more or less the rotation curve, basically. And that will disfavor, as I said, the density wave for the spiral arms where you have only one common and global pattern speed, and will favor more transient spiral arms. There's been opinions for both flavors here, but at least for the open clusters we have studied, we favor more like transient spiral arms. Okay, so I'll finish. These are my conclusions. So basically, this is I presented a method we use to detect new open clusters. It's been quite successful so far. So we detected 650 clusters in DR2 and around the same number in EDR3, and that compared to the whole cluster population known with Gaia data, this is around 50% of the whole population. So it's been quite successful. We were able to do this because we included big data framework into the analysis. So we were able to analyze together very large volumes of data. And then we use these newly detected clusters. I mean, not just this one, but they improve or the most complete. It's not complete, so the more complete population of clusters together to study the present-day structure of spiral arms and their evolutions over the past 80 million years. And that is it from my side. I will take any questions you may have. And
Thank you very much, Alfred. Very, very nice talk. Thanks a lot. So, are there any questions? Okay, I see Giacomo. You can unmute yourself.
Yeah, thank you, Thomas. Thank you, Alfred. First of all, congratulations for the work that you and Tristan are doing, among others. It's really revolutionary, the field. Congratulations a lot. I have a few questions, but I would like to start with the last slide, the 25th, I think, with the plot. If you could, because I did the next one, the 25th, yeah. Yes, this plot, because I couldn't follow. If you can iterate a bit more on this. So what is the horizontal line in this? So can you explain?
Yeah. Okay. Sorry. So wait, because this is.
So I guess that's the density wave spiral arm scenario.
Yeah. So in the density, so the open clusters were used for the same study as well by other group, and they found that the most likely explanation for the behavior they found is a density wave like spiral arm with a pattern speed like around 28, which is this horizontal line. The thing is that we were able to improve the open cluster census. We're finding also more precise ages and also more clusters with high velocities, and we were able to basically by using 4 times more tracers find not a single pattern speed, but every spiral arm with its own pattern speed that were casually like decreasing when the galactic radius is increasing, and that will be a sign of not density wave like spiral arms, but transient spiral arms.
Okay, but do you see a coherent movement, or if you take a group of an over density on a present day location of a spiral arm, and then you see a coherent movement if you go back in time, basically, as you showed us.
What do you mean coherent movement?
Coherent in the sense that you see, so I don't know, you have 50, open cluster within a certain age, right? 30 million years, you said, and then you look backwards using basically the proper motions and the astrometric information. You look at what it was at birth, right? So do they show a coherent? So do you see what I mean? So you go back to a common position, or what we say, or it's
yeah. So well, first the caveats of this is that we use these overdensity. So basically, let's focus on the green overdensity. That will be the Perseus arm. So we use individual orbits of these clusters, their birth to the birth position, and then in each of the cluster birth position, we consider that is a spiral arm at that time, and then we project forward with a spiral like a circular velocity, basically. But consider that these are clusters that are close together, like in the present day, and also they are not very old, so they are younger than 30 million years. So in the past, they are also close together.
Yeah, exactly.
They have had not time of evolving that far. But this is the same approach that this I have it here, Diaz and Lepin work out in 2005, finding the density wave like scenario was the most plausible for the explanation, and we just basically with improved open cluster census, we find opposite conclusions. And I found that already interesting.
Okay.
I mean, it's not a definitive conclusion though, but the debate is still open.
Okay, thank you. So I have Alfred, if it is okay with you, maybe after the meeting, if we can stay online, we can have a few more questions, but these are very technical, so maybe we can take it online. Okay, thank you very much. Thank you.
Next, we have a question from Dietrich. You can unmute yourself.
Yeah, thank you. Very clearly structured talk. Thank you for that. You try to reconstruct the loci of formation of the clusters. Did you also find clusters that probably did not form in the Milky Way, or is that excluded because this analysis was restricted to young clusters?
Yeah, we didn't analyze that. This is just excluded into young clusters with orbit, with disk orbits. So, yeah.
Okay, thank you.
I don't see any other raised hands, so maybe I have a question. I was just curious to know how you are planning to use the future data release of Gaia DR3, which of course will not provide new astrometry, but I was wondering whether maybe astrophysical parameters can help also in the classification and how we can include them in the machine learning algorithm.
Yeah, well, it will provide new astrometry, right? Because it will be like we go from 7 million radial velocities to 30-something million.
Yeah. Sorry. I was referring to proper motion and parallax. Yes.
Okay. So the first thing is see what happens like in the solar neighborhood where we have like 60 phase space information basically, and not just the 5D. See if I don't know, as the original idea that was testing open cluster completeness, that could be also achieved adding one more extra parameter, and that is basically what I had in mind. And then about the astrophysical parameters, yeah, I don't know, something similar to this approach here with the chemistry, but in other space it could be also done. I have not think about that, but yeah, we'll see.
Thank you. I don't see other questions over Zoom. Okay, there's one from Giacomo.
Yeah, maybe this is just a general, because when you use one of the, basically what you're doing, you're using Gaia as a discovery machine in a sense, so to discover new clusters. But of course, and this is understandable, you look for coherent groups in proper mode in 5 dimensions or 6 dimensions, depends. So that means that you are gonna looking for kinematically coherent groups in a sense, right? Which is a better definition of cluster, but there is still a lot of objects that are apparently, so I mean, you know, for example, tails, or I mean, that basically many objects that might appear, if you look at those dimensions, as kinematically not coherent, but they are still part of our interesting astrophysics. So they have big astrophysical interest, like, you know, as I said, if there are tails or streams that are living still at the same ages, but they are living stars. I mean, and they say us a lot about star formation, about this, the formation evolution of this class. So what's your
so indeed, sorry.
Yes, sorry. No, because it's difficult in that sense. While using HTTP scan, for example, is complicated because you miss them, because they're not behaving, you know, as coherently as one expects, basically.
Yeah. So basically, when we use the DB scan on the astrometric information, this is not okay, it's science, but it's data science, right? Yeah. So we're looking for over densities of this. When we include the physics, is when we require these objects to be actually like born at the same time with similar ages, chemical composition, or whatever. So this is what we introduce the physics. So to give you some numbers, the results from DBScan might result in, for the last run in EDR3, it might be like of the order of 15,000 objects. So that's a lot.
Yeah.
And then we don't look at them individually, but then we train this network with known open clusters. So we require these objects to be like open cluster-like, and that the list goes from 15,000 objects to around 1,000, and then we look at them like more or less individually. I mean, not individually, because already the neural networks like give us like a kind of a score, and then the higher score we will not look at them, but the lower score we will not look at them either. But the obvious one we do look individually at them. So indeed, there are a lot of more objects than not open clusters, but we are only in this case interested in open clusters. So all of them get removed. Also, what you say about the streams and the tidal tails and everything, take into account that we are also requiring clustering in sky position here. Yeah. So when running this DB scan, we may miss these objects because they are not clustered in sky position. Also, this DB scan, even though we use several values of our epi parameters to account for different densities, each run of DB scan is limited to one density threshold. So it will most probably get the locus of the object, which is the most concentrated part, and the other will not consider part of the object because they are in a lower density. That can be overcome with HCV scan, right? So the HCV scan is basically the same thing as DB scan, but not just one density threshold, but a hierarchy of them. So you can find different or varying density objects, but that comes at the price of exploding the false positives. And if I say that having DB scan means having a final, an initial list of 15,000 with 8 DB scan, I have not done the exercise, but I mean, it's exploding the false positive. So the analysis will be much more complicated and difficult.
Yeah.
And that's we don't do it. Also, the interpretability is less because if you have DB-scan, you can define the density you're interested in, and then you can interpret the results. With HDB-scan, since you don't define the density, just this hierarchy, the interpretability of the results is also less clear. That is why we chose DB-scan, basically.
Okay. Thanks.
Okay, I don't see any other raised hand here on Zoom. So thank you again. Thanks a lot, Alfred, for a very, very nice talk. Thank you very much. Thank you all for attending this session of the Hypatia Colloquium, and I'll just give back the word to Giacomo.
Yes, exactly. Thank you, Tommaso. Thank you for chatting. Thank you, Alfred, for the great talk, and see you next week for the next Hypatia.